So can someone confirm if you can see my screen on the chat?
Yeah.
Okay, cool. So we are going to, okay, so we are going to learn about Scikit-learn today. So Scikit-learn is basically a Python library which is used for machine learning stuff, right? So everything that is related to machine learning, you will probably find it already implemented in the Scikit-learn. So, and in your first and second assignment, we asked you to like implement a lot of things from scratch. And today we'll see all of those things, at least most of those things, are already implemented by experts, and we can basically just use their knowledge and whatever they have developed so far for our convenience. Okay, so let's get started. So the Scikit-learn, as I said, it's and also like if you don't mind, we have some Halloween dogs running around with bats and everything. So Scikit-learn is an open source machine learning library, right? It has support for pretty much everything that you need, right? So for machine learning tasks, you will basically start with taking the data and then do some processing on the data and then prepare it for any kind of learning task. Then you do the model fitting, and then you do some sort of hyperparameter tuning and evaluate the model on different types of sets, training set and testing sets and all those things. So everything like from end to end, like entire pipeline can be done in Scikit-learn. Okay, so we'll see a few of those things that you will need for your next assignment and everything else that follows. Like even your sometimes some of these things might be even useful for your Kaggle competition and everything, right? So what are things you can do? It's like you can do data pre-processing, you can do feature selection extraction, dimensionality reduction. So I think you have learned about how to do dimensionality reduction, like the algorithms for that. So all those things are already implemented in Scikit-learn. You can do classification, regression, and clustering. Those are the like three things of machine learning that you can obviously do. You can also do density estimation and model selection. Okay, so for the imports, I didn't list all the imports right here. I'm just importing all the things that I need for the data set. We will see the Scikit-learn imports as we need them. Okay, so it will be like easier for you to find stuff and when you need it. So let's import the pandas, plotting library, NumPy, and this is more stuff for plotting. So don't worry about the plotting code, but yeah. So we have imported everything. So we are going to load one data set. So, okay, so so I have basically a particular data set, which is social network ads, and we'll see some classification examples on this small data set. Like it's not a very big data set. So what's this data set? I'll just first of all load it and print it safe and some of the rows on the top. Okay, so we have, so like this social network website, right? So Facebook is there, then Google is there. All those websites, they provide ads. And what this data is about, like there are some social network ads, and we want to know whether the user actually clicked on it and purchased the product or not. Okay, so this is the data that we have. So I'm not sure if that is a true data. It might be a fake data, but okay. For our task, it's kind of it's a very small data, right? 400 rows and just 5 columns. And these are the columns. We have user ID, gender, age, it's their estimated salary and purchase. And this is the last column that we are trying to predict, whether the user actually purchased our product or not. And once we have, so this is not really like good set of rows, because like none of these first 7 people actually purchased it, but you get a point, right? So sometimes this purchase variable will be 1, otherwise it's 0. And once we know like which users are likely to purchase our ads, then we will show our ads to only those users. Okay, so this is the thing that we are trying to predict. So we have all these columns, and the purchase is one that we are trying to predict, right? So given all this 4 columns, we want to know whether the user will purchase our product or not. And So user ID is obviously not going to be very helpful, right? Because it is kind of unique for every user. It has no relation with whether the user is purchasing or not. So for prediction task, we are going to use these three columns: so gender, age, and estimated salary. Okay. So first of all, what we want to do is we want to like convert this data set so that we can train some models on this data set. Okay. So you can see like gender right now, it's not really a number, it's a string. It is written like males and females over there, right? So the scale of this age and estimated salary is different and all those things, right? So what we are going to do first is we'll convert this gender into numbers. Okay, we don't like this, like most of the machine learning algorithms, we're not really able to handle strings as it is, so we need to convert them into numbers and then we'll handle the numbers. Okay, so how do we do that? So one is that you can obviously write a small loop to figure out, like, from this column what are the unique values, and once you find out all the unique values, you can then assign a number to it. For example, you can say that male is 1, female is 2, or something like that, and then replace all the occurrences of male by 1 and female by 2, and there you have it, right? If you don't want to do all those coding, then you have Scikit-learn. You can use simple libraries in Scikit-learn. So Scikit-learn, you can import this part, like from Scikit-learn, you can have a pre-processing library, and from there you can import this label encoder. And this label encoder will do exactly the same thing for you, right? So what I'm doing is I'm just creating a label encoder, and the label encoder will, I'll just pass something to this label encoder, and it will do the transformation and we'll have a new. Okay. So now, like, everything will be now converted. So they probably assign 1 to male and 0 to female. Okay. So that's all you need to do is just, create a encoder and then call this function fit transform. So there are basically 3 types of function in encoders, right? So we have, one is called fit, one is called transform, and the third one that I'm using here is fit transform. So it's very intuitive what they are doing, right? So fit is basically what it does is it will take the entire data and it will find out what are the unique values in that data, right? So in this case, the unique values are male and female. So it will store it somewhere in their internal data structure. Transform, and also not only it will store it, it will also assign it to some number. Transform will simply replace the occurrence of male to the stored number, and occurrence of female to the correct stored number. And yeah, so, and it will return the transformed data set. Okay, so sometimes we'll see later on that sometimes, so fit only some is usually not that useful, but sometimes we need to use fit transform, and other times we need to use only transform, right? So we have to fit it separately and then transform the data set separately. So we'll see one use case for that later on. Okay, so as of now, we have everything in our numbers. Everything that we need is in numbers. We don't really care about user ID, so we are going to just drop that. Our X will be gender, age, and estimated salary, and our Y will be purchased. So this is how you do it with Python slicing. I'm just going to run this, and the next step is actually to split the data set into training and testing set. Again, like, you can do it manually, but it's better to do it with Scikit-learn because they have a better splitting function. So you can go to Scikit-learn model selection, and then you can do train test split. Okay, so this function will do the splitting for you. You just pass in your data set, which is X and Y, specify the test size, which is, in our case, it's like 0.25. Random state, it's good to specify if you want to reproduce your results, but it's not really exactly needed. There are more than this function, right? So there are more arguments to this function. Let's see if we can see. Okay, so you can see all those things, right? So particularly interesting one is like the shuffle. Sometimes you need to use. So by default, it is true, but if you want to turn it off, then you can turn it off. Stratify is another important argument. We'll see what stratification does in when we do some more scaling and other stuff. Okay. You have a question? Yeah, go on.
Yes, I just want to ask the test size here. Is it the ratio?
Yeah, it's a fraction. So yeah, it's a fraction. So 0.25 means 25%.
Thank you.
Yeah. And if you are not clear about all those things, you can always go to the documentation, right? So all you have to do for anything, like if you are confused about scikit-learn, all you have to do is just go to Google and search for it. So for example, if I'm not clear about what something means, then how I can do it is I can just type scikit-learn and then whatever function you are searching, like whatever thing you want to do, like train, test, split, right? And usually the first result will be the one that that you want, that you will be interested in. So here you can see, so you can also specify the train size if you don't want to specify the test size, right? So it says it's a float. So there it can take a float and integer both. So if you are passing a float, then it has to be between 0.0 and 1.0, which represents the proportion of the data set. And otherwise, okay, what if the integer will represent the absolute number of test samples, right? So I can just say that I want only 5 rows in my test data set, then I can just write 5 as an integer, right? So default is none, and that means its value is set to the complement of the train size. If train size, so like you have test size also and you have also train size. Typically, I prefer to use test size, but it's kind of equivalent. Okay, so you can specify train size, and if the train size is also none, it will by the default is 0.25. Okay, so we are going to specify test size as 0.25, which is apparently the default. If you wouldn't have specified it, then it would have taken the 0.25 as default. So what it returns is 4 things, like, so it will return the training set, X training, X testing, Y training, and Y testing. Okay, so CLF I have added so that just to distinguish between classification, and later on we'll also see some regression related stuff. So okay, so now if we execute this, then it will do the splitting of this data set X and Y to our X train, X test, Y train, and Y test. It will make sure that it is matching, like whatever rows I'm selecting for X, the same rows are selected for Y. Okay, so we execute it, and now the shape of the training set is 300. Okay, so I have 300 in my training data set, and the other 100 are in my testing data set. Okay, so now we have everything ready for our machine learning task, except that we see that the scales are not actually aligned. So this one is in 0-1 scale. This one age is in like 2 digits number mostly. We don't have children here. Okay, so yeah, estimated salaries is in like 1,000, very rich people. But okay, sometimes this like large gap between the scale can cause problems in your machine learning algorithms, right? So like some algorithms don't really get affected by it. For example, like if you use decision trees and things like that, it doesn't matter what's the scale of the number, but in other algorithms, it might matter, right? So there are issues related to numerical stability, and there are other issues that are related to the model performance, right? So the model will tend to learn different types of weights. So sometimes higher weights to the columns which are on higher scale, and that's really not what you want. So what's a good way of handling this is that we will scale everything to something that is reasonable. So I think you have done this in one of the scaling you have done in your first, I think second assignment. Yeah, I think second assignment you have done this. So we'll see again how to do these things in scikit-learn. So we are going to talk about 2 particular types of scalars. So standard scalar and min max scalar, but don't limit yourself to those 2 scalars. You can find more scaling. All you have to do is just search for scikit-learn scaling, and you will come up with probably more scalars than all those things, right? So typically the standard and min max scalar should do your should be enough for your whatever task you are doing. But if you are curious, then you can always search for more. So let's try to understand what all these things are. So why I just explained, like, why do we need to scale? Because sometimes you will have large values, and because of that your model will learn larger weight values and all those things. So it's not really good. We want to scale everything. So for temporarily, we are going to switch our data set. We are going to use this 4 rows data set. One of them, so first column is now number of bedrooms, which is 2, 3, 1, and 5. And the other column is the size of the property in square feet, which is in hundreds or thousands. So obviously they are on different scales, and we want to convert them into like same scale. So the one that I think you implemented was min max scalar, which was you subtract the minimum value from that column and divide it by the range, which is max minus min, and all you get is and that way, like, you can get every value between the range of what's the range? Can someone put it in the chat? So what will be the range after this transformation for min max value? Yeah, okay, 0, 1. Actually, it's written right over here. Okay, so that way, like, you can bring everything to 0, 1 scale, and you have done this programming in your assignment too. But you can do it much more in a much more easier way with Scikit-learn. All you have to do is Scikit-learn pre-processing. You import the min max scalar, create the min max scalar, which is stored in scalar mm, and I do fit transform here on the sample house data, and it will do the transformation for me, right? So it will do the transformation on both the columns. Yeah, go on. Yang, you have a question?
Yes, I have a question.
Yeah.
I am mute. I want to ask about the weight problem that you have mentioned in the exercise. You said that when the inputs have a large value, the weight may become a large value. But in my opinion, for example, in the regression problem, when we want to predict like a salary, if an input has a large value, we'll put a weight like a very little value, because the others we have to put a big weight value to have the good regression results. So I don't know why when the input is large, the weight is large also. I think it's when the input is large, maybe in the regression problem, we have to have a little weights.
It's not clear to me what kind of weights you will get if you have different scales, but the thing is, it's definitely not going to be what you want it to be.
Yeah,
so for example, sorry,
you can continue. Yeah, I understand that when the scale is not same scale, that will cause a problem for the scale of the weight. That's not what we want. We have to do the min max scale or other scaling. But it's just the phrase that a model with larger weight value is often the phrase before, when the input weight is with a large value, the weights have to have a large value. Then this sentence is not necessarily correct in my opinion. Here,
yeah, it makes sense, because it says that can result in model that learns large weight values. So yeah, I think it's not exactly correct. I agree with that. But yeah,
maybe in regression problem,
in
regression problem, if it's a little value input, we'll have bigger weight value. If it's a bigger input value, we will have a little weight value. That's my comprehension.
Yes. So yeah, I think it should be smaller weight values rather than large. Let me try to actually correct it. Because the thing is, like, what you said was correct. So for here, if I put a weight of 1, then it means it is contributing 2, 3, 1, and 5. Here, if I put the weight of 1, it will contribute 1200, 1800, 600, 2400. So
Yeah.
I'll need to significantly, like 100 times smaller weights over here.
Yeah, to
And
reduce the
that's
value.
where we will face numerical issues.
Yeah.
Okay, so thanks for correcting this. So yeah. So anyways, like we were talking about how to do it with Scikit-learn. So Scikit-learn, all you have to do is just do fit transform, and it will do this. Okay, something went wrong. How did I? Okay, I didn't execute this cell. Okay, so now we have executed, and now you can see everything is between 0 and 1, right? So the minimum value is 0, maximum value is 1. Everything else has been scaled appropriately, right? So that was the min max scaler. The other one is called the standard scaler, which does not necessarily bring everything to 0, 1 scale, but it will make sure that the mean of the data set is shifted to 0 and the standard deviation is now 1. Okay, so how do we do that? I just subtract the mean from my data set and divide it by standard deviation. Okay, so exactly the same procedure, except that I'm importing now standard scaler. And once I create the standard scaler, I do the transformation. I do call fit transform on the same data set, and it will compute its mean, its standard deviation, and do this kind of a stuff, right? So it will subtract the mean and divide it by the standard deviation, and it will print. Okay, let's see what it prints. Right. So now, as you can see, some things are not between 0 and 1 scale. Some of the values are even negative because now the mean is 0. That means some values which are less than the mean are going to be negative. And some values which are far from 1 standard deviation will have larger values than 1. Like, for example, this one has 1.52 value. The original data set, it had, what was the value? Here it was 5. Right. So the mean is, what is the mean here? 1, 2, 3, 5. I don't know. 11 by 4. And that's like, that's the mean value. And this 5 is definitely 1 standard deviation away from that, value. So this is like basically how you do it. So again, like those two scalars are at your disposal whenever you want to use it. Sometimes you want to use min max, sometimes you want to use standard scalar, and it's not really clear which one is better, and it's not even clear like which one will even like this, which one you use will have more impact on your rest of the code. So I'll suggest, like, if you have to do some scaling for your data set, you can probably even try it out, both of them, or pick one of them at random. It will, as long as your data is in a reasonable scale, it's kind of good enough, right? So especially if you have, so there are some guidelines about when you can use standard scalars. So if you think that your distribution is coming from a normal distribution, then you can use standard scalar, right? And otherwise you can also always use min max scalar. That is like another min max scalar. So so as we only talked about the large scales, so you also should do it if your scales are like very, very small, right? So if some of the numbers are like this, like 0.01 and so many zeros, 1 at 0. Multiple zeros and then 1 and things like that. If your data is in this scale also, then also you will need the scaling, because in that case you will have the larger weight issue. Here we were facing like the smaller weight issues. So yeah, either case, like in all cases, what you have to remember is that you should try to bring your data to a same scale. And yeah, once you have data in your same scale, then you can like move forward with your models and everything. Okay. So in our case, what we are going to do is I'm going to use the standard scalar. Now we are coming back to the original data set, which is this one. So I'm going to use standard scalar for these 3 columns, purely by random, right? So I'm going to use this time 2 functions. One is fit transform, and other one is transform. So fit transform, I'm going to use it on train data set, and transform, I'm going to use it on test data set. So can someone explain why am I using two different functions? Okay, no one. Okay, so recall like what fit transform was doing. So the standard scaler means that I'm going to do two things. I'm going to record the data. I'll just go through. So think about how you would implement this standard scaler, right? So you'll basically go through the entire data set, compute its mean and compute its standard deviation, and then do the scaling for it, right? So for this data set, I'm going to use fit transform. So fit is going to do two things. One is the fit transform is going to do two things, right? So first is fitting, which is it will compute the mean of the data set and standard deviation of the data set. Which data set? Only the training data set. Once I compute the mean and standard deviation of the training data set, I will do the transformation according to this rule, which is subtract the mean and divide it by standard deviation, right? For the testing data set, I'm not really computing the mean and standard deviation. Rather, I am using the mean and the standard deviation that I computed in my training data set, right? So, and why am I doing this? Like, so why I'm doing this is because like I don't want to see the test data set at all. So if I compute the mean and standard deviation for the entire data set, that means that I'm kind of, partly seeing the test data set, which is not really ideal. So test data set, I'm just keeping completely separate, right? So earlier we had done the encoding part over here. So ideally we should even do this for encoding, but here I didn't do here I did the encoding on the entire data set because I know that for entire data set the gender values are same, right? It's always going to be male and female, or whatever it's whatever it is there. I need to transform it. I need to take into account everything, right? For this kind of scaling, we don't need to take into account the test data set. Right, we can always see that I have the test train data set, and for the train data set, I'll do the learning part, which is fitting. In this case, learning is just computing the mean and the standard deviation, and I'll store that learned values and then only do the transformation for the test data set. Okay, so I hope like this is clear why I'm using fit transform and why even these people have these two different functions. Okay, so there is another third function which is just fit, which only does the fitting. We are not really using because we want to use fit and transform together for the training data set because we anyway want to transform the training data set. So now our data is in standard scale. Okay, I just updated my data set, and now so helper function I don't really need to explain things because this is something that I'm using for plotting. So I'm just going to execute it so that we create beautiful plots. Okay, so now we do the machine learning part. Okay, so what we are going to see, we are going to first see the logistic regression. You have seen this, you have actually implemented it, right? And let's see how to do it in Scikit-learn. So it's very easy, it's super trivial. All you have to do is just find out the corresponding import. So again, like I want to do logistic regression. I don't know where the import is. All I have to do is just do this. Scikit-learn. Scikit-learn, what I want to do, logistic regression. Right, there you go, the first link. Always, so there you will have the corresponding import. So the logistic regression is in the scikit-learn.linear model. Even if you don't want to even use this, somewhere down there there will be an example, right? Like over here, you can just copy paste from here, right? So we are going to import the logistic regression model, right, from Scikit-learn. I create the logistic regression over here. In the constructor, I specify all possible hyperparameters that I have, right? So let me reopen this and see what all hyperparameters it has. So logistic regression has a lot of this kind of hyperparameters, right? So one of them is penalty. Which penalty do I want to use? What's the default value if I want to, update the default value? In this case, the default is L2 penalties. I'm keeping it. You can, some of them might not, you would not have seen in the class, but you can always read the description. So C value, of course, you probably would have seen in the class, which is the regularization part, right? So the regularization coefficient, and that you can change it to a different value. By default, it is set to 1.0. Whether you want to fit the intercept or not, you can again change that value. And all these changes of hyperparameter, you have to specify over here, right when you are constructing it. Okay. The penalty is the regularization. The penalty is regularization. I don't understand. Regularization parameter penalty. Yeah. So whether you use
is the regularization parameter such as lambda times the norm of W.
So that corresponds to the which norm you are taking for.
Okay. So it's a regularization term in the loss function. So
yeah. Okay. So I can. So for example, if I want to use a different penalty, then I can specify it here. Let me actually. Penalty equal to here. So by default, it is set to L2. I can specify it to L1 if I want, or I can keep it as L2. Other hyperparameters, let's see. Do we want to fit intercept? Yes. C value, let's probably change the C value. Let's see. C equal to, let's say 0.1. I want to use lesser regularization. Okay, so so we have specified all the hyperparameters that we need in the constructor. And once you have once you have generated an instance of logistic regression, all you have to do is fit. So there are like very few functions in any classifier, right? So one of them is fit, the other one is predict. So these are like standard API for all scikit-learn classifiers and regressors and any kind of model that you are going to use. So they will all have this fit function, which basically will take the training data set and X and Y data, which is supposed to be your training data set. And you can always call the predict after training. So if you do predict before training, it will throw some error. So basically you should do it always after training. So you first fit it with this fit function, which is basically the training the model. And once you have trained the model, you'll call this predict function to get the predictions for any kind of data set. You can pass in any X values and it will give you the Y predictions for that data set. So other than fit and predict, you have few more functions. Let's take a look at them, right? So where are the functions? Functions here, right? So we are using this fit one. So other than just passing X and Y, you can also pass the sample weights if your weights are different. Predict is going to give you the predicted label. It will also, so all classifiers will also have this predict log probability and predict probability. So if you want to just, some classifiers will give you not just the single class result, it will give you the probabilities as the output. And if you are interested in computing the probabilities, then you can use this predict probability and log probabilities. So log probabilities, because probabilities are on usually very small scale, so you probably want to use log probabilities. They also have this score function, which directly computes the accuracy, right? So if I don't want to compute the predictions on the test data, I can pass in test data, X test and Y test at the same time. And it will do two things. It will compute the prediction on the X test and it will compare it with the original Y data. And it will return you the accuracy score directly, right? So the mean accuracy for the given test data and its label. So it will return you that. You can set some parameters, you can get some parameters, but I don't think you need to use that. The decision function is also something that I don't think you'll need to use it, but always. So a lot of these functions are going to be there in all classifiers that you'll see in Scikit-learn. Okay. So let's execute this. It has trained our model and now we have computed the predictions for our Y, and let's see how we have done this. So again, like you want to evaluate, you can obviously write a loop to compute the accuracy, just match every value with original Y data, or you can use, the already implemented metrics in Scikit-learn. So in Scikit-learn, we have accuracy score. You'll also have F1 score. If you ever need to compute F1 score, you can always compute the complete confusion matrix. So everything that you need for evaluation is already there in Scikit-learn. You just have to find out which import to use and how to call them, right? So I'm going to import the accuracy score, and I'm just computing the accuracy score, which is the original Y data and the predicted data. And it'll give me the accuracy for logistic regression. I'm storing it. So the other way is, as I said, you can just simply call score function and it will directly give you the accuracy. So either way is fine. And the second is confusion matrix, which will show you like which examples belong to which class and what, how many examples are predicted correctly, right? So let's see. So in this case, this is my data, right? So I have 89% accuracy, which is good or bad, I don't know. Confusion matrix is something like this. So it means like this is my zero data, the true zeros, and 67 of true zeros were predicted correctly, and one of them was predicted wrongly. I mean, I assigned one of them as label 1, which means the user actually purchased the product when it actually didn't purchase the product. But the positive data seems to have more of an error. Like it seems that I am correctly predicting 22 of them as ones, but 10 of them as zeros, which is kind of, I can see the issue is that I am not doing a good job on the users who actually purchase the ads, right? So all those things you can do it with Scikit-learn. Let's actually even do some visualization, right? So I'm doing some visualization. So I have like two graphs, one for male and one for female, but basically that's like the same line. And this is the training data, right? So logistic regression, as you might remember, it's a linear model. So our separation is this line. So 0 data are red, 1 data are green, and male one it's not really doing a very good job, but female one, it's kind of seems to be doing a fairly decent job. Okay, test data, let's see how it does on the test data. It looks like this. Again, like nothing to infer from here, but if you want to so this plotting code is just for our understanding. It has nothing to do with Scikit-learn. Okay. So let's take a look at some other classifiers that you have seen in the class. So one of them you have seen is naive Bayes, right? So again, like all the things are exactly the same. I'm just importing a different library. So now from Scikit-learn, earlier it was from linear model. Now I'm importing from naive Bayes. I'm importing Gaussian naive Bayes. Okay, so again, like creating it, and if I have any hyperparameters, I will have to specify it right here. What hyperparameters I have. So Gaussian naive Bayes has only one hyperparameter, which is smoothing, and I don't really want to change it. I want to keep it as it is. So I'm not really going to touch it. Fitting, again, like the same call, dot fit, pass the train data. And once I fit the data, then I have to test the predictions, which is by using this predict call. Rest of the things are same. Let's just see what's the accuracy and confusion matrix. So it's significantly better over here on the one. right? I'm only now wrongly classifying 7-1 data, and accuracy is kind of very high. It's now 91%. Okay, and if you do the visualization, it's not a linear one now. It's now a Gaussian one, right? So it's more like it looks more like a Gaussian distribution type of thing, right? So this kind of circles you will see, or curved, boundaries you will see. Okay, for the testing, again, it will look the same. It seems to be doing fairly decent job. And let's now take a look at k-nearest neighbor. Again, like exactly same procedure. I import it from scikit-learn neighbors, k-nearest neighbors. So again, like as I said, like if you don't know where these imports are, all you have to do is just do the search for the corresponding library. If I want to use scikit-learn, for example, decision trees, so then I can do scikit-learn decision tree, and there you go, right? So here, so decision tree can do regression also. So I'm particularly interested in classifier. So scikit-learn.tree.decision tree classifier, and the exact import is right here. Okay, so import the classifier. When you construct it, specify all the hyperparameters and do the training with fit method, do the prediction with predict method. And for scoring, you have this accuracy and the confusion matrix. Okay, so now the score is 90% for k-nearest neighbor. If we do the visualization, it will draw an even more complicated boundary. It is taking some time. So I have a question, interesting question. So for the naive base, I know what so you have implemented the naive base, right? You have also implemented the logistic regression, and you have also implemented k-nearest neighbors, all three of them. So what is happening when I do the fit function call on k-nearest neighbor? Can someone tell me? Is it doing anything, or is it just there to maintain the API structure? What is happening when I call the fit on k-nearest neighbor? Anyone?
It just calculates the distance.
With what? I'm only passing the training data set. I'm not even passing the test data set. Normalizing the data. We already did the normalization, right? Okay, I'm actually going to leave it to you to figure it out what exactly it is doing. It's so this is something that you haven't implemented in your assignment, but it's always good to know what's the right way of doing computing the neighbors and everything. So it is storing some data for the training data set from the training data set, so that it will be easier to compute the distances for the testing data set. Okay, so this is what it is doing. And if you are curious about what exactly it is doing, then always you can search and see what it is doing. So the relation boundaries are going to look more complex. So for males, it looks something like this. Females, it looks something like this. It's exactly it's still it's still the same model. I'm just plotting it for different data set. That's why it is showing different. Okay. I mean, different parts of the data set. So yeah, it is showing different. For the test data set, again, it will be same thing. Visualization part, right? So this is for male. It's exactly matching. The regions are exactly matching with what we saw in the training part. Okay, so basically the point is it's going to be more complex and everything, right? So you know where to use which model, like k-nearest neighbor, or when to use Gaussian naive Bayes, or when to use that logistic regression and whatever. So all those things that you have learned about how to pick models is still something that you need to do, but the scikit-learn will have all the things implemented for you. Okay, So yeah, imagine like how easy your assignment 2 would be if we allow you to use scikit-learn things, right? So, okay. So now let's talk about hyperparameter tuning, right? So for k nearest neighbors, I used 2 neighbors, but I don't know whether the 2 neighbors is the right number of neighbors to use or not. I want to test out other neighbors, other values for this number of neighbors. And one way of doing this is that I can just always create in a loop. Like I just say that, like, let's try with 1 neighbor, let's try with 2 neighbors, 3 neighbors, 4 neighbors, and so on and so forth. And then do all this computation of accuracy, and then pick the one which is working the best, right? First of all, so scikit-learn will do some of those things for you. And so first thing what you need to do is like you need to first divide your training data into 2 parts. One is training set and the other is validation set. On the validation set, you will be measuring, you'll be using as if that is the testing set, and you will be measuring the accuracies and everything. And whatever hyperparameter works best, then that's the one you will be using. Right. So cross validation, I think you have learned what cross validation is, right? So I'm really not really going to explain what cross validation is. You have already seen what cross validation is. So one is like you can always do simple, splitting with the train test split function that we saw earlier. Where did we see it? Right here. Yeah. So this is train test split. You can always call it again on the training data set on the X train and X Y train. And the other one is better way of doing things is you do the k-fold things, right? So k-fold approach is this one, like you divide the training data set into a bunch of folds, in this case 5 folds, use one of them as validation, the other 4 as training data set. So you train on this 4 and test on this. In another split, you train on the other 4, you test on this. So you, I think, implemented this in your first assignment. And you can always use that code, or you can use scikit-learn again. So I'm going to switch my data set. My X will be now 0 to 11. Y will be this values, A, B, C, this numbers. And I'm going to use scikit-learn model selection k-fold. Okay. So k-fold, I'm specifying I want 2 splits, so 1 and 2. And for illustration purpose, I'm going to turn off the shuffling, but you should always keep it on. And let's see what it does. Okay. So now I have 2 splits. One split has this training data and this testing data. And the other split has this training data and this testing data. Can somebody see an issue here? The output that I produce is, do you see an issue?
The first one in the training data is OC, and the second one in the test data is OC.
Yeah, so it's not really doing like good job at training and testing, right? So it is training on all C's and testing on the test data has completely different distribution, right? And in the second split also, it has kind of this kind of stuff. And so the one way of avoiding this kind of things is to use stratified k-fold, right? So what is stratification is that I will do the splitting in such a way that my Y labels will be equally distributed in training and testing data set, right? So here I have put most of my C's in my training data set and the one remaining C in my test data set. On the second one, I put all my C's in test data set and one C in train data set, which is not something that I want to do. I want to equally distribute the C's between training and testing. Same for A's and B's also. So that's called basically stratification. So you can also, so not only, so you can do it with the k-fold, and you have a stratification. I think we saw it in the original train test split, right? So you can also have stratification right here. You can say, so here, right here, stratify, right? Over here, and you can specify stratify on stratify equal to true, or so here it is not really taking a Boolean, it is taking a different value. It is, let's see what it takes. So it basically takes which column you want to stratify on, right? So sometimes your Y will have multiple columns and you want to stratify on one part of the Y, not on all the other parts, but yeah. So that's where you can specify if you want to stratify or not. Okay, so if you would have stratified, then we would have equally distributed the purchased ones, like the zeros and between training and testing data set. Okay, so back to the stratified key fold. So I'm going to do another thing which is called stratified key fold. So here I'm going to import Scikit-learn model selection stratified key fold, and if I do the stratified key fold, then like the data sets are kind of well distributed. Okay, and now let's come to the hyperparameter search. So this was about just splitting the data set. This is about creating the cross validation, splits. Now we actually need to train the, tune the hyperparameters. So one way of tuning the hyperparameters is called the grid search, which basically means that I'll specify what hyperparameters I want to tune, right? So for k nearest neighbor, I have two hyperparameters. One of them is number of neighbors, which I have written as this, but you should use Python to specify a range, not hardcode things like this. The other one is p value. So it is which norm am I using to compute the distances. Okay, so p equal to 2 means Euclidean distances, p equal to 1 means norm 1 distances. Again, that's again a hyperparameter. I'm not sure if it's worth tuning in this case, but why not? Like, I'm just trying to demonstrate how you can tune multiple hyperparameters. So stratified key fold, I'm just creating the splits and I'm calling this grid search CV, right? So I imported it from Scikit-learn model selection grid search CV. So grid search CV will take my classifier, right? The regular constructor of the classifier, the tune parameters, which is a list of dictionaries. So one dictionary will have one set of hyperparameters. You can specify more dictionaries if your hyperparameters are interrelated, right? So for example, let's say you have seen support vector classifiers, right? So some hyperparameters for support vector classifiers will make sense only if you use linear support vector classifier. Some hyperparameters of support vector classifiers will make sense if you use a different type of support vector classifier, and so on and so forth. So I don't want to specify all of them in just one dictionary. Where was I? Right. So here I have specified all the hyperparameters in one dictionary. Instead, I could do two dictionaries if I'm tuning for support vector classifier. One is like use the linear kernel and tune this parameter for them, or use the RBF kernel or different kernel and tune this parameters for them, and so on and so forth. So it's basically a list of dictionaries, and that is I'm passing it as tuned parameters. Okay, so I'm computing, so it will do the selection based on the accuracy. You can do selection based on other scores also, right? So Scikit-learn has so many different types of scores. If you want to just take a look, let's see. Scikit-learn score, metrics and scoring, right? So it has all these types of score. There's accuracies, balance accuracies, top K accuracies, average precision, F1 score, whatever you need, right? So all these scores are there for classification, regression, clustering. You can specify any value you want. Okay, so I'm specifying accuracy. I'm specifying cross validation. So cross validation again like takes a lot of different things. So let's actually take grid search CV. Scikit-learn grid search. Grid search. So cross validation. Where is cross validation? CV. So it can take the cross validation generator that we just passed, which is basically the splits, stratified key fold. You can specify default, which is none. You can specify an iteratable, which is going to give you alternatively test and training split, or you can specify an integer, which is number of fold splits that you want to do, right? So if you specify 5, then it will do 5-fold cross validation, which is apparently the default. Okay, so you can also specify an integer and it will do the stratified key-fold computation for you. So in here, instead of computing this stratified 3-fold data like this, I could have just specified CV equal to 3 and it would have been exactly the same. Okay, so it also has the same functions, right? So fit and predict. So fit will do all the hyperparameter tuning and it will select the one which is working best on the validation sets, and then it will train everything on entire training data on that hyperparameters. Okay, so let's do the tuning. It's quite fast. So if you want to check out which were the best hyperparameters, you can always call grid search dot best parameters. Again, like all those things you can already see in here. Okay, so attributes. So CV results will have the cross validation results. The best score, if you want to compute, it's here. Best estimator, you can get best parameters that we just printed, which is, yeah, the best parameters apparently is 5 number of neighbors and you use norm 2 for distance, right? And if you want to use the entire result, then if you want to see the entire result, let's see the entire result, right? So grid search dot CV result, and I want to see the mean test score and standard deviation for the test score, and I'm going to print for every all the values, right, in the CV results. Okay, so let's see. For so now I have results for all the parameters that I've tuned, right? So this is the values that I get for accuracies, and you can see that the phi2 right over here is 0.897, and that is the best. Okay, this is also 0.897, but we defined this model decided to use phi2. Okay, so again, you can just directly call predict on it. It will do the prediction on the best hyperparameters. And there you go. You can also compute the complete classification report. Again, it's a different metric. We have been printing till now confusion metrics. Now we can also, so there is also another thing called, if you want to take a look at the evaluation, then you can also print the complete classification report, in which you'll get the list of, precision, recall, F1 score, support, and all those things. All different types of accuracy, macro average, weighted average, and so apparently it's not really different, but yeah. So that's the way you tune hyperparameters. So we just saw grid search CV. There is another one which is called a random search CV. If so, grid search will do the training on every hyperparameters, like so 1 1 1 2 2 1 2 2 3 1 3 2 and so on and so forth. But like, let's say if you have large number of hyperparameters to tune and your training takes a lot of time, in that case you don't want to do grid search CV because it will take like a lot of time. Then you can do random search CV. It will randomly pick hyperparameters and do the training, and at the end of a certain number of iterations you can always pick which one worked best for you, right? So that's another way of doing things. Let's search for it. Scikit-learn random search. Yeah, randomized search CV. There you go. Right. So that's another way of tuning hyperparameters. Right. So it's kind of similar to what we just saw, grid search CV, just that the process is different. Right. Okay. So let's close all this. So we have tuned hyperparameters, and yeah, that kind of completes our classification part. Let's take a look at a couple of things that you can do with regression. Right, so regression, I'm not really going to show you everything. So I'm going to use a different data set, which is much smaller. It's this kind of a data set where I have position and salaries. So position is like different positions, the level and the salaries, right? So that's what I have. And I have only 10 rows for this. So I'm not really even going to split them into training and testing. I'm just going to show how to fit things if you want to do regression. Okay. So I'm going to use only the level and salary for, I'm going to use only level and predict the salary as my Y values. Okay. So I'm just going to run a function for visualization. And regression model, you have learned linear regression so far, right? So linear regression, kind of same thing. What you want to do is just linear scikit-learn, linear model, linear regression. If you want to specify hyperparameters, this is the place you are specify. So kind of, I don't know, penalty or something. If we want to specify it, let's see what hyperparameters I have. It has fit intercept, true, number of jobs, positive. I don't know. It doesn't seem to have penalties apparently. And never mind. So if you have any penalties, then that's where you specify. Again, like the same function, it's fit. It will do the fitting part. If once you fit the part, if you want to test it on a different data set, then this is the testing data set, and you call the predict, and it will return you the predictions. Okay. So we are only going to see the fitting part because we don't really have a testing data set for such a small data set. So let's see how it fit, right? So this is the linear regression. The line it is going to fit is this. So this was my data. It's not really doing a very good job because this is not a linear related data. It looks like a polynomial. So I'm going to do a polynomial regression. So how do you do polynomial regression? Is that you convert your data into polynomial. So you have till now x, you can compute x square, x cube, and x3, and then you do the linear regression on top of it, right? So that's what I'm going to do. So for scikit-learn, I can do scikit-learn pre-processing polynomial features, right? And it will compute the polynomial x for me. So I just specify the degree as 2, and it will and then I call the fit transform on x. So it will compute the 2-degree x values, which is basically the levels. So levels, right? So it will have 3 values. It should have one as the level itself, one is the level square, and one is constant, right? So it will compute the 3 values. Constant, basically constant will mean like 1 values. Then I fit the linear regression on this polynomial representation of x. And let's see how it does, right? So now a 2-degree polynomial seems to be doing a better job at regression over here. Again, the functions are still the same, like fit function, and for prediction, predict function, all the model evaluation that we saw, again, it's exactly the same. So it doesn't change anything, right? So we have seen classification, regression, and everything. We have some time. If you want, we can just, so I listed all those things as future materials, but apparently it seems that you have already studied support vector classifier and decision trees. So if you want, we can see how they work. So same thing, like scikit-learn SVM, we imports SVC, support vector classifier, specify the hyperparameters over here, fit, predict, and then compute all the scores and metrics and everything. So let's see how it does. Yeah. So the accuracy is 89% for support vector classifier, linear classifier. If you want to see the boundaries, it looks kind of like this. Testing one, kind of the same, like the linear boundaries. And support vector classifier with different kernel, non-linear kernel. It has better accuracy. It has 93%. And it will also show you why it looks better. Let's see the distance boundary. So distance boundary is kind of nice, better distance boundaries, right? So that's why it is doing a better job at test data set. Okay. You have also seen decision tree classifiers, I think. So decision tree classifiers, again, so decision tree classifier has a lot of hyperparameters. So I'm using criteria here as entropy, but you can actually specify a lot of different hyperparameters, right? So you can see the minimum number of samples to split, minimum number of leaves you want to have, minimum max number of features that you want to consider, So here you can actually even say that if your data set has a very large number of features, you can say that, don't consider all the features, only consider like square root of the total number of features, or log of total number of features, or things like that. Random state, max number of leaf nodes that you want to specify, all those things you can specify, and all those things you will need to tune it at some point of time. Okay, so that will be I think somewhere there in your assignment 3. So let's see how it does on our data set. So without any kind of tuning, I'm just using the default parameters and see how the performance is. It's 92%, it's fairly decent accuracy. And the prediction, so the recent boundaries, the regions, looks like this. Okay, so that's how the decision trees work, right? And random forest, I'm not sure, have you seen random forest in your class already? Yes, okay, so let's see random forest also. Again, so number of random forest is kind of an ensemble model, right? So you can import it from Scikit-learn ensemble. So it is basically combining a lot of different trees and creating a combination of those trees. And I have a number of estimators set to 10 over here, right? So let's see how it does. It is also doing 92%, kind of same as distant trees, but okay. Distant boundaries like that, it's hard to distinguish between distant trees and random forest as of now, but typically random forest should do better than distant trees. Okay, so that kind of ends our tutorial on Scikit-learn. So you have the notebook, and let's see if you have any questions you can ask, otherwise we can end the tutorial. So basically now you should feel confident about the entire machine learning pipeline. You should know how to do pre-processing, how to do encoding, and how to do scaling, and how to import different classifier or regression models and compute the predictions for them, do hyperparameter tuning, and yeah, and do the model evaluation and everything, right? So all those things you can do with Scikit-learn. So random state parameter, it's not really a hyperparameter. It's basically, so some of these machine learning algorithms, they involve some random computations in it, right? So they'll need to compute some random numbers at some point of time. So what will happen is that if you use different random states, then you can get different results, right? And so the random state is mainly for reproducibility. So if you train something on decision trees and then you want to reproduce that result, then you can use the same random state, and it will do the exact same training. Otherwise, it might do some different training, right? So first time I did the splitting on some different node and with some different feature. If I have ties, then I have to break the ties with random choosing and everything. So I'm basically, a lot of these algorithms have some, random computation involved. And if you don't specify your random state, then every time you train, it will give you a different model and your results will differ. So if you want to reproduce the result, then you specify a fixed random state so that you will always get the same results. It's not really a hyperparameter, it's more like for reproducibility. Okay, any other question? Okay, so I'm going to stop the recording somewhere. Okay.